I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video. When we are talking about leaving groups, particularly the halogens being used as a leaving group, then you are thinking about a nucleophilic substitution reaction. In general, the rule is this: a good leaving group, Lg, a good leaving group is a weak base and it's coming from a strong acid, and because of its size, it can accommodate a negative charge well. If it can fulfill these three categories, it's a good leaving group, and you would see it come about in terms of a nucleophilic substitution reaction. When we're talking about our halogens, you know we have fluorine, the chlorine, bromine, and iodine. The leaving group tendency is better in terms of iodine and it's worst for fluorine. Iodide makes a good leaving group, fluoride makes a horrible leaving group. It's so horrible that you won't normally see it even as a leaving group. Keep this in mind as we look here at this reaction. If I have here ethane, CH3, CH3, and we hit it with ionizing radiation and in the presence of bromine diatomic, you know you'll get a free radical reaction and you'll generate ethyl bromide. In a nucleophilic substitution reaction, we hit it with a hydroxyl. You know you're looking here at a halogen, which is like this, and then you have your nucleophile, which we'll represent as this nucleophile. It's going to do what you know, a substitution reaction, particularly an SN2 reaction, and you'll have inversion of configuration and all of that. Your end result here will be the nucleophile will displace that halogen group and the halogen will come off here as a leaving group. Normally in these type of reactions you'll see chlorine, bromine and iodide, but you never see fluoride or fluorine because its leaving group ability is just horrible. When you do complete this reaction, you end up seeing an alcohol form, CH3, CH2OH, plus your bromide ion or anion. Now look over here, I'll show you something. We know in terms of leaving groups, fluoride is the worst, iodide is the best. Look at everything here with regards to this general rule. I have hydroiodic acid and it dissociates into iodide and H+. In terms of a conjugate base, this right here is very weak, but it's coming from a very strong acid. Hydroiodic acid is the strongest in terms of a hydrogen halide. It's a very strong acid. A very strong acid has a very weak conjugate base. Now look over here at hydrofluoric acid, and you know you're going to get your fluoride and then you'll have your H+. This right here is a stronger conjugate base, and I'll just write here stronger conjugate base, but this right here is a very weak acid. A weak acid has a strong conjugate base, a strong acid has a weak conjugate base, but a weak conjugate base serves as a better leaving group because it can accommodate a negative charge better. Why can't this iodide accommodate the charge better, a negative charge better than fluoride? Because of its size. It's large. The atom is large. This right here is small and it's highly electronegative, and so it's not going to serve as a good leaving group whatsoever. You will remember over here that weak conjugate bases will come from strong acids or strong conjugate acids, but those weak conjugate bases will then therefore serve as better leaving groups, and they will be the ones which will be frequently seen in nucleophilic reactions. We will close this video with just a demonstration of how the SN2 reaction will look appropriately with regards to the stereochemistry which is involved. You have over here the carbon, and you have the bromine, and you have a hydrogen. You have another hydrogen over here, and you have this which is your CH3. Hence we're looking at ethyl bromide. Nucleophile here will be the hydroxide. We're looking here at our hydroxyl, and it's going to attack from the back, and this will get displaced, and you'll have inversion of configuration, which I'll write here as INV and then CUNFIG, inversion of configuration. When you have the inversion of configuration, you have over here your hydroxyl attached from this side, and then everything flips like an umbrella being turned upside out, or umbrella being turned inside out. And let's complete this molecule right over here, and this is exactly what we're seeing over here as our end result, and our leaving group over here will be our bromide, and this would be the end of this reaction. And you're not going to name these either with an R or an S, because you're seeing that this right here is not a chiral center. You have two similar atoms attached to carbon. These are not chiral in terms of anything, so we don't have to even worry about R and S configuration. Just you're noticing here only the inversion of configuration coming about because of an SN2 reaction, and it's nucleophilic, and bromine over here, or bromide, as you see over here, will serve as a very good leaving group. It's able to, because of its size, handle that negative charge. It's also a weak conjugate base, but it's come from a strong conjugate acid, which is HBr. HBr is a strong acid, and when you dissociate it, you have H plus and Br minus. The bromide is a weak conjugate base, but this right here is a very strong acid. That right there is the end of this video. Thank you.